Back at me, I give a move. Step in the block, love, I know where to go.
Assalamualaikum and greetings to Dr. ASYRAF and my fellow friends. Today we will be presenting about an analytical method called gravimetric analysis. The title of our journal is Investigation of High Temperature Stability and Thermal Endurance of Silicon Potting Compound by Thermogravimetric Analysis. In this presentation, we will include introduction, the analyte investigate, the sample preparation technique, the analytical method used, the observation, and the conclusion.
So, the introduction. The high temperature stability and thermal life of silicon resin-based potting compound SC3 used in the aerospace application for electrical insulation is investigated thermogravimetric analysis (TGA) in an inert environment. Thermogravimetric analysis is a well-proven and fastest method to characterize the thermal degradation phenomenon and predict the thermal endurance of materials. A typical TGA weight loss is analyzed as a function of time or temperature to determine material degradation kinetic parameters under accelerated thermal aging. Thermal stability in the material is studied for its thermal degradation behavior as a function of time and temperature. Analyte investigated. Silicon-based compounds are progressively in demand for soft electronics and electrical and electronic device, encapsulant and packaging applications. It is essential to understand the long-term thermal stability in high-temperature applications and the prediction of thermal endurance or time to failure to limit their usage at high temperature.
Next is about sample preparation technique. A two-component silicon potting compound, or known as SC3, is obtained based on a hydroxy-terminated polydimethyl siloxane system with nanosilica as a reinforced filler. The hardener is based on a dibutylene dilaurate catalyst. First of all, 10 grams of paste, which is part A, is taken in a mixing bowl and 0.6 grams of hardener is added into it. It is mixed thoroughly by hand for 6 until 8 minutes. The samples were allowed to cure at room temperature for 24 hours. The table here shows the mixing ratio of paste with a hardener in parts by weight, where 100 grams of paste and 6 grams of hardener was used. Let us move on to the analytical method used. The non-isothermal TGA experiment at different heating rates are performed using a TA model TGA55 thermogravimetric analyzer. About 10 mg of finely powdered sample size is placed in a small platinum crucible for each run under a nitrogen atmosphere with a 60 ml/min flow rate. During the heating, a change of weight loss due to time and temperature is collected automatically by the instrument and is determined through the TA Universal's analysis software. The experiments are repeated under identical conditions to check the reproducibility of the result. Thermal stability in the material is studied for its thermal degradation behavior as a function of time and temperature. Degradation in a material depends primarily on the reaction temperature, heating rate, residence time, and particle size. So, in order to determine the activation energy of thermal decomposition, isoconventional model-free method have been used.
Next, I will explain about observation and result part. The first one is thermal stability. Thermal degradation profile of compound SC3 are recorded in the temperature range from 30 Celsius to 900 Celsius at varying heating rates of 10, 20, and 30 Celsius per minute, and the results are shown in Figure 1. Thermogravimetric TG curves on the SC3 sample are shifted to higher degradation temperature as the heating rate increases. This is a general phenomenon for thermally activated process. In the initial phase of heating, the SC3 compound's degradation is minimal up to 350 Celsius at all three heating rates, which could be attributed to the loss of volatile contents present in the SC3 compound. A rapid weight loss in the SC3 compound is started only after 360 degrees at all three heating rates. The primary degradation process of the SC3 compound occurs in the temperature range of approximately 400 Celsius to 610 Celsius at all three different heating rates. After this temperature, the weight loss decreases slowly to the final degradation temperature, and the half-life or T-half of SC3 compound at steady heating rate is mentioned in Table 2. Based on Table 3, the residual mass determined at 900 degrees is found to be independent of heating rates. This residual mass is correlated well with the inorganic filler quantity used in the SC3 compound. The first derivative of the TG, which is DTG curve obtained for the SC3 compound, are shown in Figure 2 at different heating rates. The TG curve are used to determine the Tmax, which is the temperature at which the maximum rate of weight loss occurs of the compound at different heating rates. In general, the heating rates affect the DTG curve position and the maximum decomposition temperature. With increasing heating rate, the onset and the endset temperature of degradation are also increased. From the DTG plots, it is observed that below 350 degrees Celsius, the rate of the thermal degradation is low, but after 350 degrees Celsius, it increases rapidly as the temperature increases. The maximum degradation rates are achieved in the temperature region of 500 to 600 degrees Celsius at all three heating rates. After the maximum, the decomposition is low again until it finishes at the final temperature of degradation. The onset T1, Tmax, and the endset Tn temperature of degradation of SC3 compound are shown in Table 3. In aerospace application, the SC3 material is intended to use in most electronic device, which will be inside the vehicle at an inert atmosphere. However, the thermal stability of the SC3 material is also carried out in an air atmosphere. Compared with the inert atmosphere, the TGA at the air atmosphere has shown less thermal stability. This is shown in Figure 3. The higher weight residue in the air at 900 degrees Celsius is attributed to the reaction mechanism which forms silica during the thermo-oxidative degradation mechanism, as mentioned in the literature. Next is evaluation of activation energy. The model-free kinetic analysis gives a dependence of activation energy on the degree of conversion. The activation energy at different conversion is evaluated by model-free FWO, KAS, and Kissinger method and summarized in the Table 4, with the adjusted R2 values of linear radiation. The activation energy calculation by the KAS method use the temperature for a given degree of conversion, but not the temperature for maximum weight loss. According to the FWO method, the activation energy is calculated a little higher than the KAS method. Figure 4 shows for the KAS plot, A. FWO plot, B. Kissinger plot, C. and dependency of activation energy on the degree of conversion, respectively for 0.1 to 0.9 degree of conversions. It is mentioned that if the activation energy depends on the degree of conversion, then EA-KAS and EA-FWO may not be the same. Both the FWO plot and the KAS plot show nearly parallel at different heating rates of 10, 20, and 30 degrees Celsius per minute for different conversion value, ranging from 0.1 to 0.9. In the experiment, low residual content, which is we can see in the table 2, present of the tin catalyst, and a sharp increase in activation energy limiting to a maximum in the range of 122 until 128 kJ per mole is observed. This indicates that the ionization of thermal depolymerization of polysiloxane chains may be due to nucleophilic cleavage of SiO bond as proposed in figure 5.
Last but not least is the thermal endurance prediction of SC3. The objective was to predict the thermal endurance also at high temperatures in SC3. The equation has been used to predict thermal endurance or time of failure at high temperatures in the range of 100 to 350 degrees Celsius. Graph above was plotted to evaluate thermal endurance at various temperatures for SC3. From the graph and the table, SC3 withstand approximately 3.6 minutes and 350 degrees Celsius, whereas at 100 degrees Celsius the thermal endurance of SC3 is 122 years.
In conclusion, we can conclude that the thermogravimetric analysis is a simple and easy tool for understanding the kinetics of degradation reaction. The electrical putting compound SC3 has been investigated for its thermal degradation behavior in an inert environment using non-isothermal TGA. The activation energy calculated using variety of method, revealing the complex mechanism of reaction that occur during the degradation process. The thermal endurance or time to failure of material is also determined, and the result indicate that the material can be used safely at 100 degrees Celsius for several years, whereas at 350 degrees Celsius, the time of failure is only 3.6 minutes.
That is the end of this presentation. I hope you can give us a big thumbs up and share this video. Thank you for watching. Bye!